Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Get started, I know other people will be trickling through. It's my absolute pleasure to introduce Professor Hal Dome, who's here with us this week on loan from the University of Maryland. I've had the pleasure of knowing Hal since he was a PhD student at USC, and seeing his career flourish since then. So Hal is a recognized leader in both the NLP and the machine learning communities. He did some groundbreaking work in his PhD on very elegant and simple structured prediction models for NLP that have gained a lot of following. And Hal is also very noteworthy, a devoted educator, cares a lot about issues like augmenting the visibility of resources for academics. I often find myself looking up his course slides online, maybe some of you do as well, on topics like graphical models and reinforcement learning and a bunch of different NLP topics. And if you don't do it already, it's a great idea to follow his now famous NLPers blog, which has a ton of really great insights and also active discussions with a bunch of people in the community who participate on it. Now, before I hand over the floor to him, I just want to plug another event that Hal will be holding tomorrow. So at noon tomorrow, Hal will be giving a about 3-hour tutorial on domain adaptation. And this is one that he gave at ICML recently to very high acclaim. And please come and join us. Bring your lunch, and we'll try to start around noon and have a break midway with some snacks. Okay, so I give you the floor.
So thanks for coming. Thanks for having me, and thanks for coming. So I have this very vague talk title, which is essentially because I don't want to have to decide what I'm going to actually talk about until like the night before. This is joint work with a ton of people. So the students are along the bottom. Those are, of course, the ones who did most of the real work. And then Lyle, who's sort of my linguist friend, he and I overlapped at Utah for a couple of years. He's now at University of Hawaii. John, Daniel, who's my advisor, Dan Klein, and Jason Eisner. So some of this stuff with Jason is the new stuff. So I should warn you, there's going to be sort of a mix of stuff that you might already know and stuff that I know that you haven't seen unless you've either reviewed papers or are reviewing papers or something like that. So hopefully there will be something for everyone. I'm not going to say too much about why we care about language. I think we all care about language, right? So we communicate, we spend lots of money doing things like this. Maybe if you're sort of a cognitive scientist, you think that it tells you something about how the brain works. Half of my life I spend as a machine learning guy. So even though, this is sort of an NLP talk, it's, content-wise probably actually mostly machine learning. And then obviously, you guys know better than anyone that there's tons of data available. Also sort of, just why is it hard, right? I mean, I think the classic reason why we think NLP is hard is because things are ambiguous. Saying that I went on an interview with my laptop versus I went on a date with my laptop, this is a very subtle semantic difference. Sometimes there's world knowledge that we use to interpret sentences, like John wanted to commit suicide, he got a rope. Sort of at a very high level, this looks like some weird topic drift. You have no idea why these sentences are next to each other unless you make some fairly large inference about the purpose of this rope. And then one thing, I guess I'll talk about this more tomorrow, but we like to talk about language as being something, but it actually changes a lot. So here are 4 example sentences from different domains of text. And your job, so this is the interactive part, you have to guess what these are from. So the first sentence is, many factors contributed to the French and Dutch rejections of the proposed EU constitution. So what source of text might this sentence be from?
News.
News? Yeah, news. Okay. Latent diabetes mellitus may become manifest during thiazide therapy. Yeah, biomedical or Medline or something. Okay, I said he could put what he wanted. I didn't believe. This one's hard. This is actually movie subtitles. I forgot to mention in yesterday's post that I trimmed a huge hedge that spans the entire length of the front of my house and is about 3 feet across. This is my mother-in-law on IM. And actually, my wife told her recently that I've been using this as an example in talks, and I was worried that she would get really pissed off, but she actually thinks that it's awesome. So if you want data like this, I have a huge corpus of sentences exactly like this. This one's actually not that bad. You can understand this one. Most of them, I have no idea what she's talking about. Okay, so the sort of view of NLP that I'll be talking about today is this NLP as transduction view. So we get some sort of input, which is often text but needn't be, and we have some sort of output, which again is often text but needn't be. And our job is to map or to transduce from this input to the corresponding output. So this comes up in translation, so our input is some French sentence, our output is an English translation. In summarization, our input is a collection of documents. Our output is a short summary of those documents. In syntactic analysis, we get a sentence and we're trying to produce some sort of syntactic analysis of this sentence. There's been sort of this big paradigm shift in NLP, which I'm sure you all know, right? So the old story used to be, hire knowledge engineers or linguists and have them encode things about language in the world. Now, instead of paying them to encode things about the world, we just pay them to annotate data, and we learn some sort of models over the data. And I guess the hope is that we get some reuse out of this data that we wouldn't have gotten before. And then there's sort of this recent trend toward unsupervised approaches, where we ask ourselves, well, where do we get this information that rope is a means of suicide? And so if you Google, or I guess if you Bing for, is Bing actually a verb? It is. It's supposed to be a verb? Okay. So if you Bing for killed himself by and look for the autocompletion, you can figure out that rope is actually a pretty good autocompletion of this. But again, it requires some computational encoding of this human knowledge, right? We have to know that this is the right thing to search for. So sort of the first half of this talk is going to be about mostly supervised learning stuff, and then the second half of the talk is going to be mostly about unsupervised learning stuff. And the main question that I'm interested in here is how to get encodings of human knowledge in a way that can actually help NLP systems. Okay, so this is my Structured Prediction 101, and I've been using this slide since 2004 just because it took me so long to make it. We're trying to learn some function that maps inputs to outputs. So think, French sentences to English sentences. So here are a couple examples. So we might have X as I can, a can, and we're trying to do part of speech tagging. So say pronoun, modal, verb, determiner, noun. But of course, the challenge is that there are lots of other possible outputs, and we're trying to select just one from this really large set. So the same thing happens in parsing. So we're trying to draw some sort of tree over the sentence, but again, there are tons of possible trees. In coreference resolution, so now you can see how old the slide is. We have a bunch of mentions of entities, and we're trying to do coreference. So obviously, coreference is temporally, you have to pay attention to time, but I didn't when I made this slide, so you get to think that Clinton is still the president. And then translation, we get some sentence like Mary did not slap the green witch, and we say, Maria no dio una bofetada a la bruja verde. So this is Kevin Knight's favorite translation sentence. So, and I don't speak Spanish, so if it's wrong, I apologize. Okay, so I'm going to always refer to X as the input space, Y as the output space, and this process of going from input to output is decoding, even though I hate that term. I tried to get it changed like 5 years ago, and it didn't catch on, so I'm stuck calling it decoding. Anything else. Transduction would have been fine. Or mapping. Okay, so I think the central claim in a lot of work in structured prediction, where we're trying to produce these complicated structures, is that we have to ask ourselves, like, why do we actually think structure is important? Like, we put a lot of effort, both from a modeling perspective and from a computational perspective, into enforcing some notion of structure. So we must think that it's important, and so why could this be? So there might be correlation among outputs. So let's say that I'm looking at everyone in this room and I'm trying to classify whether you're an NLP person or a machine learning person. Okay, so let's see if I can come up with a good example. So I look at Chris Cork and I'm like, the features that I can extract from Chris suggest to me that he's an NLP person, right? So I don't know, but I'm pretty confident that Chris is an NLP person. It's the glasses or something. And so then maybe I believe that people like to sit next to like people. So I look at the people surrounding him, and now I get additional evidence that maybe they're NLP people also. So, just because I don't get that many features about someone sitting next to Chris, the fact that they're next to Chris gives me extra information. So these are two sort of more NLP-ish examples. There's another case, which is the case that the way that you're being evaluated at the end of the day sort of forces you to pay attention to structure. So an example here that I like to give to my class when I'm teaching machine learning is to say, okay, at the end of class, I'm going to give you a final exam. And there are going to be two parts on the final exam. The first part is going to be about the first half of the semester. The second part is going to be about the second half of the semester. And now, if I tell you that when I grade you, your overall grade is going to be the average of your grades on these two parts, you're going to study roughly equally for the first half and second half of the semester. But if I tell you that your overall grade is going to be the max of your score on these two parts, then you're only going to study one of them, right? It would be stupid to waste your time studying the other. So this is a case where there's some structure in the problem, right? I've broken the problem down into two halves. And because of the way that I'm evaluating you, it would be stupid for you to not pay attention to the structure. Okay, so a lot of what I'm going to be talking about sort of for the first half is trying to understand whether these issues are actually important, and if they are important, how to deal with them. So the first observation that you have is that we often run into these really obnoxious computational problems in structured prediction. So the way that most algorithms work is we take some input x, some output y, and we try to learn a scoring function that says, that gives a high value when xy is a good pair and gives a low value when xy is a bad pair. And then at test time, we get, say, an Arabic sentence in as input, and we want to find the English sentence as output that maximizes the score function. So this is the classic argmax problem. It's usually some sort of nasty combinatorial optimization problem. You can sometimes solve it by dynamic programming, but then you have to throw away all the features that you want to include. So then you run like beam search or A star, something crazy. So here's the second audience participation part. So this is going to be a really simple task, so it's sort of part of a translation task. So I give you a bunch of words. I've randomly permuted their order, and I ask you to put them back into order. So this best search, this refers to searching over an ordering using a beam search with a pretty wide beam, but not complete. So it's definitely not optimal search. And then the score is some sort of model score. So the system thinks that the best reordering of these words is I say better than Bart, Madonna, comma, which I think that we probably all agree is not right. So what should it be?
Depends on how you feel about Bart and Madonna.
I said Madonna better than
Where was the comma?
I don't know.
It's say I say. Like
I say Bart, comma.
no, better Bart than Madonna, I say, or say I.
Oh, my slide screwed up. But yeah, you're right. Better Bart than Madonna, comma, I say.
Madonna than Bart.
It could, but Bart is obviously better than Madonna. Okay, and so the model actually does prefer this. If you feed in this sentence, it says, oh, that is a better sentence. I just couldn't find it. So here's another example. I won't even give you the random order. I'll just give you the order that the model chose. So it's and so could really be a neural apparently thought things as dissimilar firing to identical? Okay, so we could sit here for a while you try to figure this out. So it's supposed to be, could two things so apparently dissimilar as a thought and neural firing really be identical? So, this is it's kind of a silly example, but, even for us, the 6-word sentence is hard. The 30-word sentence is nearly impossible. So we really do need to get around this issue of argmax search, I think. So these next 2 slides are basically a year and a half of my life boiled down into 2 slides. So this was the stuff that I did in grad school. So the idea was basically we want to integrate the learning process with the search process, and at each, okay, so we can think of the search process as constructing some output incrementally. In this case, it's a translation example. And each step in this process is going to correspond to a decision made by a classifier. So here we have a French sentence, which I know there are errors. I apologize. It should be le, not apostrophe. But I don't speak any of these languages. So at this point, we've maybe covered the first 3 words. We're still trying to translate le croissant. And our English hypothesis, going left to right, is the man ate. And so we ask ourselves, what are the things that we can do next? So one thing we could do is grab the whole phrase le croissant, translate it as a croissant. We could grab the word le and translate it as a fox. I could grab the word croissant and translate it as happy. I could grab the word croissant and translate it as I could grab the word le, translate it as So right, there are tons of possibilities. But the idea is that sitting at this decision point, I'm going to have some classifier that's deciding between these sets of options. And the idea is that the set of options available to this classifier, although large, is much smaller than the set of all possible translations. So I only have to enumerate over a much smaller set of things. So this leads to a chicken and egg problem. Essentially, when we start asking ourselves, what should this classifier do? So the reason it's a chicken and egg problem is we have to define what it means to be good. Okay, so I have a classifier, he's searching along, and at some point he's trying to make a decision. Okay, what does it mean to be a good decision? Well, a decision is good if I take that decision, and then I let my classifier keep wandering along, and at the end it gets to a good translation. Okay, so the notion of a classifier's good decision depends explicitly on that classifier's future actions. It also depends on my past actions, because I've already produced part of a translation. How did I produce that part of the translation? Well, I ran my classifier. So my classifier is getting me to where I am, and it's getting me where I want to be. And I'm trying to optimize my decision here with respect to my own performance on these 2 parts. Okay, so this is a chicken and egg problem. We're computer scientists. What do you get when you get chicken and egg problems? You do iteration. So we start with some guess as to a hypothesis or a classifier, and we incrementally learn more and more each time. So we make all of our past decisions by the previous iteration's classifier. We're going to make this one decision by our current classifier, and then for each of these actions, we're going to run the previous iteration's classifier to get a full output, and then compute like blue score, whatever loss function we want on that output. And then this loss will feed in to training the current iteration's classifier. Okay. Okay, so you can prove something about it. I don't really care. Okay, so here's a little example. So this is a summarization example. So a user goes to Bing and says, give me information about Falklands Islands War. Of course, he doesn't actually say that, right? He just says, like, Falkland War. But, we know what he really means. And so we get a bunch of documents, and then he gets sad because that's far too much information. So we throw it through a summarization system, and now he's happy again because he can read about what he cares about and then move on to the rest of his life. So for those of you who aren't in summarization land, the predominant way in which you do this is to grab a handful of sentences from these documents and glue them together as some sort of output. So this is sentence extraction. But especially if we're trying to produce very concise summaries, just pulling out sentences might not be a good idea. We'd like to also drop words and phrases and things like that. So this is often called document compression. Okay, so here's how we're going to do it. So we're going to take every sentence in our document set. We're going to parse it. So this is a dependency parse. And then essentially what I'm going to do is I'm going to grab onto this word 8 and like yank it down. So the tree ends up looking, wow, my slides are, I would love to blame PowerPoint, but this isn't even PowerPoint. So we're going to yank it down and then we get a tree that looks like this. So it's just going to be visually more pleasing. So we're going to parse all of the sentences. They're each going to get a parse tree. Of course, in practice, the parse trees won't all be the same, but this was a copy and paste job. And we're going to create a summary by incrementally adding words to the summary. And the way that we're going to do this is we mark the root of each of these trees, so this is basically the head verb of the sentences, as a frontier node. And then each step in the search process corresponds to selecting a frontier node, adding it to the summary, and then marking all of its dependents as future frontier nodes. So we run this process. At some point, we hit some word limit, say 50 words, and then we report what we extracted as our summary. Okay, so here's some example output with a 40-word limit. So this is if you run sort of off-the-shelf sentence extraction plus some sentence compression after the fact. Not the sentence compression I just described, other people's sentence compression. So we get something like Argentina and Britain announced an agreement nearly 8 years after they fought a 74-day war, a populated archipelago off Argentina's coast, so there was some compression error there. Argentina gets out the red carpet. Compression error, official royal visitor since the end of the Falklands War in 1982. So this is what you get if you run our thing. So Argentina and Britain announced to restore full ties 8 years after they fought a 74-day war over the Falkland Islands. Britain invited Argentina's Minister Cavallo, I don't know, to London in 1992 in the first official royal visit since the Falkland War in 1982. So, okay, obviously I'm showing you this example because it makes us look good. And so one way that you can evaluate these things is you can ask humans to produce summaries. You can measure how many times the humans mention different aspects of the data. So in this case, all 6 annotators mentioned something about diplomatic ties being restored. And then we can go and see if our summaries mention these things. So if you do this and you score it by how many humans wrote this down, the sentence extraction gets 13. We get 24, so this is awesome. But of course, this is just one example. But if you do this overall, we do get some significant improvement. So I think this is Rouge 2 scores. So this is if you do 100-word extraction, and then this is if you do this vine growth thing up to 100 words. So you do sort of markedly better. Okay, so I guess it was more than 2 slides, but that was basically like the last 2 years of grad school for me. So this is some new stuff that we've been doing that has some similar ideas, but has sort of a different goal. So this is sort of my caricature of how NLP works these days. So we get some training data. We throw this training data into some like super fancy learning algorithm. In this case, we're doing parsing. So this super fancy learning algorithm gives us a really slow parser. Okay, like really slow meaning like parses a 25-word sentence in about 5 hours. And so we're completely dissatisfied with this. So we do a bunch of crazy stuff with hand-built heuristics to make this thing faster. So we do some A star maybe we do some pruning, who knows. We do all sorts of crazy things. And at the end of the day, we get a fast parser, which of course is what we wanted in the first place. And so the question is like, well, why do we go through all of these steps? Let's just stick in a fancier learning algorithm and directly learn a fast parser rather than going through this intermediate step of learning a slow parser. And the idea, I guess, is that statistical learning has largely revolutionized how NLP people build models, but it really hasn't affected how people make those models fast. And so our hope, I guess, is that the successes that we've had here can sort of carry over. Okay, so what we're going to do is we're going to specifically optimize a parser for some reward function which looks something like accuracy plus alpha times speed, where alpha is some user set parameter. And I guess the fact that I'm calling this reward maybe hints at how we're going to actually go about doing this. Okay, so the thing that makes this hard, of course, is that as you're going along and as you're parsing, you can get a good sense of what you're doing from an accuracy perspective. It's much harder to get a good sense of how you're doing from a speed perspective until you've completely finished the parse. Okay, so we're going to work with a prioritized parser. So it's a parser driven by a priority queue. And a large part of the reason that we're doing this is because search problems driven by a priority queue are sort of much broader than just parsing. So people use it in controls land, for robotics, and a bunch of other stuff. So here we have a sentence, I can cans. And we have a parse chart. So at this point, we've parsed these 4 words. And we have a bunch of items on our agenda. So we know that on the basis of what we have in our chart, we could construct a verb phrase from 2 to 4, so covering cans. We could construct a verb phrase from 1 to 3, so can. Or I could construct a sentence from 0 to 2, so I can. And these each have some priority. So in this case, there's 7, 2, and 1. Who knows where those came from? But I'm going to take the top one off. I'm going to fill in the corresponding cell in the chart. And then I'm going to update my agenda by adding the new options that have become available as the result of this action. Okay, so next I'm going to pop off this VP from 1 to 3, fill in the cell in the chart, pop off a VP from 1 to 4, and then finally pop off this sentence from 0 to 4. And then at this point, I have completed a sentence, so I now have the option of stopping and returning the sentence that I've found. Okay, so I guess the question when we start thinking about this is, what tools do we have in our toolbox, and why don't those work for this problem? Or if they do work for this problem, then we need to find a problem for which they don't work. So you could think about this as a reinforcement learning problem. So I have an agent. He is exploring the world of parse trees. At each step, he has a bunch of actions that he can take, and those actions correspond to selecting something from the agenda and putting it on the chart. We can simulate the environment. The environment is just the parser. We can run this thing, and then at the end of time, we can see, well, what was the overall reward, which trades off this accuracy and speed, and then reward the agent for getting high reward and punish the agent for getting low reward. So this seems like maybe a good idea. The problem is that if you apply vanilla reinforcement learning to this problem, it does nothing. The search space is just far too large for this agent to sort of randomly explore possible parse actions and ever hope to create a good parse tree. It's actually hard to get it to even create a parse tree at all. Like, a lot of times it just sits there creating constituents willy-nilly for like days on end. Because we don't get this sort of immediate reward, we only get the reward at the end of the day, it is sort of unable to get off the ground and start going in an interesting direction. Okay, so then there's this other field called inverse reinforcement learning or inverse optimal control, or it's sort of related to apprenticeship learning and stuff like that. So the idea there is I'm trying to train a system to drive a car. So what I'm going to do is I'm going to put a human in the car, and the human's going to drive, and then I'm going to watch what the human does, and I'm going to try to mimic whatever the human's doing. So I could potentially take my gold standard parse tree that I have in my training data and use this to simulate a human going through the parsing experience. Okay, so the problem is that we can do this well if all we're going for is accuracy. Okay, so if we know the true parse tree, We can easily deconstruct it into the series of steps that's required to produce that parse tree, and we'll get like 100% accuracy. The problem is that I don't know how to compute the oracle tree for accuracy plus alpha times speed. Okay, so if you think about it a little bit, maybe you can see why. Right? So the problem is that the gold standard parse tree, while optimal from an accuracy perspective, might be actually quite crappy from a accuracy speed trade-off, right? Like if you really care about speed, probably the best thing to do is just to parse your 20 words as an S node that branches to each of those 20 words. It's going to be a completely terrible parse tree. You'll basically get one constituent right, but it's fast. So we no longer have a single oracle, which is the standard view in reinforcement learning. So we have what I'd call an expert. Right? The expert is the guy who produces the correct parse tree, but this expert isn't actually optimal for the reward that we care about. Okay, so what we've been doing is we've been looking at some sort of hybrid between inverse reinforcement learning and vanilla reinforcement learning, where we allow the expert to guide things sort of initially so that this poor agent isn't stuck exploring this ridiculously huge space. But then over time, we sort of turn down the effect that the expert has so that the learned model can attempt to be better than the expert that we started out with. Okay, so I'm not going to give you numbers because it's actually really hard to interpret these numbers. I can say your agent's overall reward was 6.295 for some value of alpha, but I mean, that means nothing to us. So I'm just going to put smiley faces and frowny faces and sort of neutral faces. Okay, so we looked at a bunch of different settings. So this is how much do we use the oracle. So the oracle is the guy who's telling me, according to the true parse tree, the accurate parse tree, what should I do next? So if I don't listen to him at all, I spend all of my time exploring random stuff, and I do total sad faces. Okay? If I listen to him exclusively, for the most part, I do badly. And this is basically because if my alpha is 0, so if I only care about accuracy, then obviously this is a fine thing to do. This is basically exactly what we did for the summarization example. But for any alpha that's not 0, we basically only learn to be an accurate parser, and we end up being super slow at the end of the day, which is exactly what we're trying to avoid. But if you do something where you believe the oracle, say 80% on the first iteration, and then 0.8 squared percent on the second iteration, and 0.8 cubed percent on the next iteration, and so on, you can now start to actually get something that is guided to the right part of space, but doesn't trust the accurate expert too much. Okay, so now what are these columns? So there's this question of what we can do about reward. So immediate reward basically means that when I make a parse decision, I immediately tell my classifier whether that was a good thing or a bad thing to do. And this is good thing or bad thing with respect to the accurate oracle. Okay, so this is basically training a parser to do, or training a classifier to do parsing. I can also do completely delayed rewards. So this means that I go along and I don't get my reward until the end, which would be the more sort of standard reinforcement learning thing to do. Or I can do discounted reward, which is sort of another standard RL thing where you say, well, early decisions are more important to me than late decisions. So it turns out that in the settings that we were looking at the point when I made this slide, which was 2 weeks ago, these two, there didn't seem to be a difference. So whether you do immediate reward or whether you do delayed reward doesn't really matter. It turns out if you crank up alpha high enough, so if you care more and more and more about speed, immediate reward starts to suck. So this sort of turns into a yellow face. And this guy stays happy. Okay, so it seems to be important to use this expert when he's useful, but to not trust him too much, because trusting him too much basically either means this top row or this first column, both of which are bad. Okay. All right. Okay, so this was, I guess this is also in the flavor of trying to get things to be fast. But the question that I want to sort of ask here is going back to this issue of what role does structure play. Okay, so here I've drawn out two conditional random fields. So we're doing something like part of speech tagging. So we get a bunch of features of the words that we're trying to label. We're trying to produce parts of speech along the top. And we can assume either a dependence between adjacent parts of speech, or we can assume no dependence between adjacent parts of speech. And so the advantage to the structure, of course, is that it's accurate, but it's slow. You have to run dynamic programming. The advantage to the bottom one is that it's fast, but you don't get to use this information about your neighbors. So what you could hope to do is think that, I'll use the laser pointer, right? So this node here is getting information from its two neighbors. But at test time, we don't actually know the value of these two neighbors. We're only inferring the value of these two neighbors. And how are we inferring them? Well, we're inferring them from the corresponding inputs. Right? So we could kind of hope that if I simply give this node access to more of the input, I could get the quality of the structured model at the cost of the independent model. Okay?
That's overlapping features.
Yeah. Which is fine, sort of, in CRFs, right? It would be bad in HMMs. But it's even bad in CRFs. So there are basically two questions here. So if we move to this independent model, the two questions are, is this expressive enough? So can I actually generate the types of output sequences that I want? So in machine learning land, this would be called approximation error, because I'm approximating this model using this less expressive model. And then the second issue is it easy to learn? So this is an estimation error. So the thing to notice is that when I add these additional edges, I'm adding extra features to the model, which means I'm adding extra parameters to the model, which means I'm going to need more data to accurately estimate these parameters. Okay, so moving, say, from either of these top models down to this bottom model, I'm adding a huge number of features, which is going to come at the cost of some estimation accuracy. Okay, so, but we can do something about this. So here's a little example. So we take a bunch of features. We train a CRF on part of speech tagging and named entity recognition. We get like 95% and 75%. And then we train the same independent model. This should be ILR, not IRL. But we train the independent model using the same features. Part of speech accuracy drops to like 92. Named entity accuracy drops to about 70. Okay, so now we can add our additional features coming from neighboring words. So we have the same feature set, we just apply it to a larger window. Part of speech accuracy recovers almost all the way, not quite all the way. But named entity recognition accuracy actually goes down. And this is basically because we have lots more data to train a part of speech tagger than to train a named entity recognizer. So it's just overfitting more. So what we're going to do instead is we're going to take our labeled data, we're going to train a CRF, we're going to use that CRF to label a huge amount of unlabeled data, which is going to hopefully counteract this estimation error issue. And then we're going to learn an independent model on this automatically labeled data. And so if we do this, in part of speech tagging, we recover all the way. In named entity recognition, we don't get quite all the way back. But we're at least not doing worse than before. We only recover about half the performance. Yeah?
Are you just dribbling out the features in F2, or you're actually starting to have more clever aggregate features?
No aggregate features, just larger window. And actually, for these experiments, F1, I think, is actually already applied at a window of one word on each side. And I think F2 is applied 2 or 3 words on each side. We basically fiddled with it to get the best possible performance for these numbers. And it's different between part of speech and named entity recognition, but I don't remember what's what. So actually, Percy did these experiments, so you can ask him. Or I guess you could read the paper. Okay, so at the end of the day, we're trying to go from this CRF with the small window features to this independent model with the large window features. And we want to analyze the error that we induce when we go from the CRF to the independent model. Okay, so we're going to do this in a couple steps. So in the first step, we're going to ask ourselves, how important is it that we... Okay, so when we do inference in a CRF, we do, say, Viterbi search on the output, right? Which is going to produce what's usually called a coherent output. Alternatively, we can do marginal decoding, where we directly predict the label of each node by marginalizing out all of the neighbors. Okay, so this is going to be our marginalized CRF. Then the next thing we can do is, instead of marginalizing out these neighbors, we can link their corresponding outputs or observations to the variable that we're trying to predict. So this is basically our features applied at an infinite window. And then finally, we cut off the ones that are too far away. And so each step here introduces a new sort of error. So the first thing that we lose is coherence. So when we do Viterbi search, we know, for instance, that determiner followed by verb is just not going to happen. Whereas here, we don't know what we actually predicted for this first word. So if marginalizing over this and marginalizing over everything else, verb looks good here, we're perfectly happy to say determiner followed by verb. The next step is we get nonlinearities. So we usually think of conditional random fields as linear models. The output is a linear function of the input. But once we've marginalized out our neighbors, this essentially looks like some sort of neural network where here's our output unit. These guys make some sort of hidden units, and then these are our input units. And because of the nonlinearities introduced in the marginalization, we get some sort of nonlinear prediction. And then finally, we're losing some global information, right? We're no longer getting information about this last node. Okay, so the question is, can we measure where the error is coming from and where is it bad? So this is one of those cases where what came out was not at all what I expected would happen. You can prove that the error of the total thing is the sum of the of these errors. So you can compute this coherence effect by measuring mutual information on the edges. It's basically one of these KL divergence terms. It turns out for part of speech tagging, this is very, very small. And if you look at the error of this top model versus the error of the second model, there's no difference in actual performance. It's a little bit higher for named entity recognition, and we do get a little performance drop for losing coherence. So this is mostly because we're using like a BIO encoding, and when we do marginal decoding, it doesn't enforce the natural BIO constraints. So to get this next one, we can train a truncated CRF. So I'm not going to say exactly how that works, but this results in a huge drop in performance in named entity recognition, so like over 3%, which is the majority of the error. So to get this last step, we can train a marginalized CRF. For named entity recognition, this doesn't seem to make a difference. So the thing that was really surprising to me is that I would have expected that coherence was the most important thing, perhaps followed by global information. And it never really would have occurred to me that there even are nonlinearities in this model. It's just so foreign for me to think of CRFs as nonlinear models that I never would have expected this to happen. But the main effect really does come from the nonlinearities. So one natural thing you could do is say, well, instead of training an independent linear model, maybe we should train a neural network for making each of these predictions, and then maybe we can recover these nonlinearities. But we never tried it, so I couldn't tell you. Yeah, Chris?
Also stack hidden layers, so say I did some sort of jackknifing on my data. So first I train a classifier that looks at each word or that predicts each word independently, and then the next level classifier can look at the prior level classifier's predictions. It feels like if you stacked it high enough, it's basically running like a message passing algorithm, right? So, but maybe only 2 layers is enough to recover a lot of the nonlinearities.
Yeah, so I think William Cohen's done some stuff like this. But yeah, I mean, it's exactly the same thing, right? The magic, which I don't know, I mean, maybe it actually makes sense, right? But the magic is that the value that we get at this node is basically acting as some sort of summary of the information sitting below it. And we'd much rather get that summary rather than getting all the information because it's too much to deal with.
But the original goal is to make the thing efficient. Isn't the marginalized CRF nice and efficient? Or maybe I misunderstood it.
No, because to predict with the marginalized CRF, you have to run forward backward. It's posterior decoding. Okay. Yeah, so it's not until here that you don't have to run dynamic programming. Okay, so I thought this was a little bit surprising. I wouldn't really have expected that. So here are the actual results. So this is the amount of unlabeled data we use. I think it's like thousands of, no, I don't know. Millions of words, maybe. It's a lot. I don't remember exactly. So the blue line is the structured model. This is the structured compilation approach. So for part of speech tagging, we recover everything. For named entity recognition, we don't get quite all the way there, but maybe if we had more data, we would. Or maybe you need a wider window. And for parsing, we get most of the way there. I should say that this is parsing where the training data is 10% of the tree bank, not the full tree bank. If you do the full tree bank, the picture looks more like this. So I put in the good picture. Okay, so any other questions on this stuff? All right, so I'll mention as an aside, Slav Petrov had a pretty cool paper a year or 2 ago on question parsing, where they basically do something just like this, so they kind of reinvent it. I'm not saying this in like an annoying way, but if you think this stuff is interesting, you should take a look at Slav's paper. They do something similar, and it works really well, in more of a domain adaptation setting than in a semi-supervised learning setting. Okay, so I want to talk a little bit about where all our data comes from, because this is really what makes all of these models work. So we get some sentences, we get linguists to annotate them with syntactic structures, we estimate a probabilistic context-free grammar, we use that to parse new test sentences, and if we have annotated data, this works really, really well, right? And of course, trees look more like this, not like the thing that I showed before. There were a couple papers last year that sort of had the same observation. So we can get an English tree bank and estimate a context-free grammar from it. We can also get a French tree bank and a Spanish tree bank. And if we look at these, we might notice that a lot of the constituent structure looks very similar, right? They all have S goes to NP-VP. They all have NP goes to determiner noun. Sure, English does this weird thing where it puts adjectives in the middle and everyone else puts adjectives at the end. But overall, the sort of general structure is very similar. So why don't we just tie these all into one big model and do some big joint estimation? And so if you do this over these 8 languages, you can get about a 21% average increase in performance for parsing each of them individually. So this is really interesting, but these languages are actually very similar, at least structurally. Maybe not Slovene and Chinese, but actually you don't get that good results on Slovene and Chinese. So one of the easy observations is that all of these sentences or all of these languages are basically subject-verb-object languages. They don't have high degrees of variation in word order. So we'd like to take this a little further so that we can capture languages like Japanese and Hindi. So here we have a bunch of sentences in different languages. And in the first 2, the verbs come before the object, so we say they're verb-object. And in the last 2, the verbs come after the object, so they're object-verb. And then we can also notice that in the first 2, the add positions come before the noun, so they're prepositional. And in the last 2, the add positions come after the noun, so they're postpositional. So if you talk to linguists, they'll say This is referred to as verb object implies preposition, and postposition implies object verb. So here it is more graphically. So this is a bunch of languages in the world, color-coded based on whether you're verb object or object verb. So English is up here. It's a red dot. Japanese is over here. It's a blue dot. So this is verb object. This is preposition versus postposition. So English has preposition, so it's red. Japanese has postposition, so it's blue. So I can sort of hit the up and down arrow a bunch of times, and you might notice that there's actually quite a strong degree of correlation between these two features. We obviously have more data for verb object than for adposition, but they're highly, highly correlated. So this data comes from this World Atlas of Language Structures. It has about 2,000 languages and about 140 features, but most of it's missing. It's only about 15% known. So I'm actually going to skip this part. So the question is, can we use this information to do better syntactic modeling? So this is a very, very small example. I'll do the larger one later, but I don't have exact numbers for it. So what we're going to do is we're going to take a parser, and we're going to give it a little bit of typological knowledge. And the knowledge that we're going to give it is that articles precede nouns and adpositions also precede nouns. So this means that it's prepositional. So the language we're working with is Portuguese. We're also going to add information about whether a particular part of speech is an open class or closed class part of speech. So if you don't do anything, you get about 5% accuracy, which is really crappy, not really useful. Not that this is particularly useful at 40%, but it's better than 5. If you just add the open-closed information, you jump from about 5% to about 20%. And then each of these typological rules individually gives you about another 10%, and then they stack. So we overall get some sort of accuracy around 40%. And this is using no lexical information about the language. It's just using these two typological rules. And we've done experiments with more rules, and things keep getting better, but it does asymptote somewhere around 55. So that was sort of a trial case. The thing I really want to do is something like this. So we have English parse trees and a parse. Oh, yeah.
Sorry. I mean, do you want me to just wait till the end?
No, you can ask.
So, I mean, so you added these typological rules, but there's also a class of work of where you add like 10 annotated sentences or something to. Do you have any thoughts of which is better?
Yeah, I can show you the results. So basically, if you so we didn't compare against 10 annotated sentences. We compared against a set of seed words. Yeah. Okay. So basically what happens is if you add the seed words, you get about 50%-ish. And then when you add these things on top, it climbs up to like 55-ish. So it doesn't climb up that much. But what we realized after the fact is that for this 50% accuracy, most of it is coming from just getting those seeds right rather than having those seeds generalized to other things. And so if you measure your performance on the non-seed words, you get a graph that looks more or less like this, but about 5% higher. I actually had a blog post about this a couple weeks ago. So this is something that I think is actually really hard about working in this domain, is comparing models that use seed lexicons versus models that don't, because once you add seeds, if you say, okay, my seed is a determiner, then like all of a sudden I get like every occurrence of the word the right. And should I really get credit for that? I don't know. So certainly seeds are helpful. So in order to get about this 40% level, you need something like 2 seed words for each part of speech. So you can decide which is more. We got our seed words from Wikipedia. Okay. So here's what I want to do. So I trained an English parser. I've extracted an English Potawatomi, I think that's how you pronounce it, dictionary, which I would have talked about if we had had more time, but I didn't talk about it. So you can do dictionary mining and extract dictionaries from comparable data. And of course, I want a Potawatomi parser. So what I'm going to do is this approach that we had back in 2008. So here we're trying to simultaneously learn to solve 2 tasks. So I'm trying to solve a syntactic analysis task that's part of speech tagging and base phrase chunking, and a named ND recognition task. Okay, so I have some sentence. I'm not showing you the words. It'll come up in the next animation. And I'm going to tell you that this is the correct syntactic analysis. And now I'm going to ask you, which of these possible outputs for named ND recognition do you think is the right one? Okay, so does the question make sense? Okay, who likes the first one? No one likes the first one. Why not? Yeah, there's a person with a verb in his name. That would be a little weird. Okay, what about the second one? Who likes the second one? Rule kind of likes it. Anyone else? Minimum Bayes risk says a rule is wrong. Christina kind of likes it too. It's not bad, right? I mean, we have two proper nouns, noun phrase, there's a person. Seems totally reasonable. Okay, who likes the third one? Not many people. Who likes the fourth one? Everyone likes the fourth one, right? So, oops. So why do we like the fourth one? Well, in the fourth one, entities are subsequences of NPs, and proper nouns are subsequences of entities, right? So we sort of believe that these are two things that should be obeyed by pairs of syntactic analyses and named ND recognition. So the actual sentence is George Bush spoke to Congress yesterday. So this one is right. You could easily come up with other sentences for which this one would be right, though. I don't think the others could ever be right. Okay, so we have this black box algorithm. So basically what we do is we learn a parser on labeled data. We learn an entity recognizer on labeled data. They don't have to be the same data. We run them both on unlabeled data. We look at examples where their performance on the unlabeled data agrees with whatever constraints we think should hold about these two tasks. And whenever they agree in this way, we say that, oh, they must be correct. So I add those examples back into the training data for both, and I repeat this process. So under certain assumptions, you can prove that this works in the way that you would expect. And so it actually works in practice, too. So the obvious baseline is just vanilla self-training, because this is kind of what it's doing, versus learning with these hints, and it seems to work pretty well. So this is amount of unlabeled data, and I think this is named ND recognition performance.
So this is based on these hints where we don't. You're formulating some rules. How many rules did you have, and how hard were?
Oh, those were the only two rules I had.
The only two. Okay.
Yeah. And this was part of the very first NSF proposal I ever wrote, and those two rules were in the proposal, and we never bothered to try to come up with more. We thought a little bit about trying to learn more. But I never hand-coded anything else. Yeah, Chris?
You're looking at the one best assignment from each of these components and then
Yep.
seeing if it agrees?
Yep.
But you could search for deeper assignment, search through the packed representations and find situations where they agree.
Yeah. I mean, you could probably set up some sort of probabilistic model where you basically intersect the two finite state machines. Actually, in the paper, so this was done using discriminative learning, blah, 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 mumbo jumbo. But in the paper, there are actually some results about doing it with HMMs, because with HMMs, you actually can easily intersect these things and compute various things. So for instance, there's a term that's being hidden in here that you can actually compute efficiently on HMMs by running an intersection. But yeah, didn't try it. There are lots of things we could have tried that we didn't do. Oh, I'm missing a slide. Shoot, hold on. Let me see if it's there and yeah, there we go. It was just out of order. Oh, wait. Okay, so we're doing basically the same thing here. So we train an English parser, but restricted to the dictionary, the English side of the dictionary that we extracted. We run this on some unlabeled Potawatomi data. And then we look at the parses that agree with whatever linguistic rules we believe should be held in Potawatomi. And then we add these sentences with their full vocabulary. So now we get some sort of vocabulary expansion to the training data and retrain the parser. So it's basically the same idea, except we're not retraining the English parser every time because it'll probably just get worse. And it's slow. So there's, of course, this danger that it just doesn't do anything. And so I won't give you numbers. This is something that someone's been doing very recently, but it does look like it's actually doing something reasonable. Now, of course, our parsing performance on Potawatomi is very terrible. And it's pretty hard to come up with reasonable baselines that aren't straw men. So we've compared against various unsupervised learning algorithms and stuff like that. We've compared against some simple rule-based algorithms that are based on the linguistic constraints that we're using to constrain the parser. And it seems to be doing substantially better than both of those. But right now, the reason why I'm saying looks promising is because we've only been doing it on a fairly small amount of data. So the English parser is on like 10% of the tree bank. And so it's unclear how things will scale when it gets better, when it gets bigger. But I think it's going to work. So maybe if you're reviewing for NACL next year, you can see the paper. Or if you don't see the paper, it means that it didn't work. So, of course, what I want to do at the end of the day is have some big model that explains everything in the world, right? So we have these linguistic features. We have these typological features. We have annotated tree banks in some languages. We have a bunch of parallel data. So I have some Bible data that spans about 100 languages. We have raw text, which spans, Wikipedia. So like, again, another 100 languages, but a disjoint set of, not disjoint, but it's not a subset superset relation. And so most of the stuff that we've been doing has been either looking at using the linguistic features together with the annotated tree banks, or together with the raw data, or the linguistic features together with the typological features. But really what I want to do over the next couple of years is tie this all together and have some big joint model. So with that, I won't even conclude because I figure either you've been paying attention or you haven't. But I think that the two things that I'm really interested in on the supervised side is what role does structure play and how do we make things efficient? And then on the unsupervised side, I'm really interested in getting some specific forms of linguistic information back into these models, especially in this massively multilingual setting. So with that, I'll stop and take questions.
Right now, you're treating accuracy as just another side objective, which you can weigh with respect to accuracy, to efficiency versus accuracy. If you treat it as a constraint problem, such as you have this many machines that have this many cycles, that seems like it would complicate things, but hopefully it could also help.
Yeah, so we've thought about it, right? Because the real world problem usually is I want to optimize performance with some constraint on time. And I guess what it comes down to is I don't know how to optimize that. Part of the problem is that, so we've done some other things in vanilla classification settings where the game is, like let's say I'm a mail server and I'm trying to detect spam, right? So someone connects to me, I get their IP, right? And I'd like to throw them off as quickly as possible if I think they're spam. But I can wait a little longer and then I get their header. And then I can wait a little longer and I get their body. And I can wait a little longer and I can do image recognition on whatever image is in the attachment or whatever, right? And so we've looked at this, do as well as you can with the constraint on the amount of time. The thing that becomes tricky is that even if you can get a reasonable estimate of the amount of time that things will take, there's always some variance, right? So what you often, or what we've been looking at is to say something like, I want to make sure that the expected amount of time plus like one standard deviation is within some constraint. And of course now sometimes you won't violate this constraint, but that should only be like 5% of the time, or if you believe that things are Gaussian. So yeah, I'd like to do it. I don't have any great ideas about how to do it. Another thing I've been thinking of, just as food for thought, is the following question. So I want to learn something. I have some amount of money. I can pay people to annotate data, or I can pay some cloud service to run some fancy learning algorithm. All right, so I have this trade-off between cycles and data. And there actually is a fixed dollar cost on these objects. And so how do I trade off between these two? So we've been looking at this a little bit, but I don't really have any interesting results.
If there's any more questions, just please come up afterwards.